Namaste and welcome back to the lecture on linear algebra through geometry. In the last lecture we looked at the idea of linear combination of vectors in an n dimensional space, a vector space Rn, and we looked at that special linear combination of a set of vectors which was giving us the 0 vector, and if the only combination which gave us the 0 vector was basically by putting the scalars to be 0, then we said that the set of such those vectors were called as a linearly independent set of vectors. And we also looked at how to check whether a given vector is actually a linear combination of set of vectors, which means you populate the set of vectors. Let us say I have the set S of vectors u1 u2 un, and I have another vector say u. I want to check if u can be written as alpha 1 u1 plus alpha 2 u2 plus alpha n un. All I did was I just put those u1 u2 un as the columns of the matrix A, and then I wanted to solve Ax equal to b, where b was basically the vector u vector that was given. If I can find x1 x2 xn such that Ax equal to b holds, then we say that the vector b, the vector u on the right hand side was basically a linear combination of the column vectors of the matrix A. That means the column vectors correspond to the vectors which were in the set S. And we also looked at whether, in order to find out whether a system of in a set of vectors is basically linearly independent or not, we again did the same thing. What we did was we defined a matrix A in which we put all these vectors, the given set of S vectors, or from Rn we put those vectors into the matrix as the columns, and then we tried solving Ax equal to 0, the homogeneous system of equation. If this homogeneous system of equation had only trivial solution, then we said that the given set of vectors which actually were used as columns of the matrix A are linearly independent. If not, we said that is a linearly dependent set, and we also made a concluding remark saying any set of vectors which contains the 0 vector is a linearly dependent set, and we also said a subset which a set of a set which contains only one vector is a linearly independent set, provided the vector is a non-zero vector. So, we had that, right. In the current lecture that we are going to have, we are going to look at the idea of basis and dimension for a vector space. That means you are trying to find out, we are in the hunt for finding out a set of linearly independent vectors whose linear combinations is going to give us all possible vectors in that particular vector space, right. That is what we are going to look at, and that is what we are going to call as basis. But before that, let us define a few things. So, the first thing that we want to look at is basically what we call as span of a set of vectors. We want to look at span. So, let us say S be a non-empty set, non-empty subset of a vector space V, non-empty subset of vector space V. Right. Now, what we want to do is we want to define the span. So, the span of S is basically the set of all possible linear combinations, the set of all possible linear combinations of vectors in S. Right. So, we define the span as, okay, let us put this as definition. Span is nothing but the set of all possible linear combinations of the vectors in S. Let us take some example. Suppose I define S to be the first of all, let us first take the vector space. I am going to look at the vector space V. I am going to call the take R3 as the vector space, and I am going to look at S to be the set of these two vectors, which is basically 1 0 0 and 0 1 0. Yeah. Now, what we have is for alpha 1 and alpha 2 real values, real, the set of all possible linear combinations, the set of all possible linear combinations of vectors in S correspond to S correspond to, let me define that span of S, which is nothing but alpha 1 into 1 0 0 plus alpha 2 into 0 1 0 alpha 1 alpha 2 real. Yeah, this is what we have. So, what is the span of S? So, the span of S is basically the set of all those vectors which are given by alpha 1 alpha 2 0 or alpha 1 alpha 2 real, right. If you see, the third component is 0 here, therefore, the span of this set of S vectors is going to be basically the x1 x2 plane. Is that clear? The span of S is going to be the x1 x2 plane. Now, let us look at second example, example 2. Suppose I have this S vector which is basically 1 0 0 0 1 0 0 0 1. Now, what is span of S? Span of S is basically the set of all these vectors which is alpha 1 alpha 2 alpha 3. This is correct for alpha 1 alpha 2 alpha 3 real. Why did we do this? How did we get this? We basically took alpha 1 into 1 0 0 plus alpha 2 into 0 1 0 plus alpha 3 into 0 0 1. So, you got alpha 1 alpha 2 alpha 3 for all values for all alpha I is real. Now, what does that mean? So, the span of S, if you see, is going to be the entire R3, right. So, this implies we are going to get all the vectors in R3. So, I am going to say span of S is entire R3. Right. Yeah. So, now let us extend this idea to, let us say n component vectors in n dimensions and stuff. So, suppose the set S is equal to, let us say u1 u2 etc., let us say uk, and let V be equal to Rn. There are k vectors, n component vectors that I have taken, and the vector space that I am going to look at is basically Rn, right. So, the span of S is basically given by the set of all those vectors which is sigma alpha I ui for I is equal to 1 to k, and alpha I is all real for I is equal to 1 to k, the set of all these vectors that I am going to get, right. Now, what is more interesting is what is the geometry of this span, that is what we are going to look at now. So, if I look at this, say span of a single non-zero vector in Rn, let us say the vector u, let us say the vector is basically u1 u2 etc. un. Let us take this, S is equal to the singleton u1 u2 etc. un, n component vector please do not confuse this with that u1 vector, where that u1 vector itself had an n component vector. This is a single vector where the components are u1 u2 un, right, n component vector. So, this the span of this is basically what it is, the multiples of, so span of S is basically the multiples of let us say alpha u, that is it, right. This is the set of all these vectors which is alpha u for alpha real. Now what does this mean? This is going to be scalar multiple of the same vector. That means this is going to have a geometry which is a straight line passing through the origin. So what are we going to say? Span of a single non-zero vector is basically a line passing through the origin. Right. Now what is interesting is we have not even actually spoken about whether the set of vectors is in S is going to be linearly dependent or linearly independent. We have not done anything, we have just looked at span of a set of vectors. Okay. So what are we going to look at? The next one, span of any two linearly independent vectors in Rn is a plane passing through the origin. Right. Yeah, we are going to look at span of any two linearly independent vectors where of course n you take it to be 2 and so on. R1 you do not have, I mean you can't define a plane and stuff, so okay. And what is even more interesting is if you look at the okay, let us make this note. Most important stuff as about span, let us look at this. So any subspace, first of all, any subspace of a vector space V that contains the vectors u1, u2 etc. uk, this subspace which contains this vector u1 u2 uk must definitely contain the span of u1 u2 uk, because the subspace contains the linear combinations of all possible linear combinations of the vectors. So what we are going to say, must contain the must contain all possible linear combinations of u1 etc. uk, which is basically the span of u1 u2 uk. Yeah, that is basically the span of u1 u2 uk. And what is interesting is the span of a given set of vectors where S is non-empty subset of a vector space V, non-empty subset of vector space V, span of S is the smallest subspace that contains S, smallest subspace containing S. That is the most interesting observation that we make. The span of a given set of vectors is basically the smallest subset which contains, that is basically the compact set which is going to, I mean compact set not in the algebraic sense, that is the most compact box that you are going to have in which contains all possible linear combinations of S, and therefore it will also contain the vectors S, is that okay. So this is the smallest subspace which contains that S, okay. Now we have a question, we know what a span, we know this we have studied the idea of linear independence and stuff. So what are we going to do is we are going to look at we are going to ask a couple of questions. So let us say let S be a subset of a vector space V let U be any vector in V. Now we have two important questions which arise here. What is that? The first question that we have is basically, does there exist a linear combination in S that is equal to U? What does that mean? We are going to ask, can U be expressed as a linear combination of the vectors in S? Question 2, if such a linear combination exists, is the linear combination unique? Now this question of linear combination being unique or not is directly looking at the set of vectors S, and it is equal, it is the same as asking is the set of vectors in S linearly independent. So this is like saying, in other words, is S a linearly independent set? The question that we have, right. In order to answer this, we look at a very important definition which is called basis for a vector space. Basis for a vector space. So let us see what it is. So let V be a vector space and let B is equal to, let us say, B1, B2, etc. Bk be a subset of V. Right. So we are going to make this definition, we are going to say the following. What is that? B is a basis for V if and only if A, B spans V. That means the span of B vector is the entire vector space V, and B is a linearly independent set. So what we have? A set of vectors or a subset of vectors from a vector space will be a basis for the vector space if and only if the span, the set of all possible linear combinations of this set of vectors B that we have taken, it spans the entire vector space V, and B is a linearly independent set, right. That is what this actually means. So let us look at some examples. Let us consider V to be R2, the vector space that I have V is R2. So I am going to have, I need to find out a pair of linearly independent vectors in R2, so that you know the span of these two vectors is going to be the entire R2. So, B1 I am going to take this as 1 0 0 1 is a basis for R2. Second example, again I am going to take V is equal to R2 and I am going to take the second basis 2 1 1 2. We know that 2 1 and 1 2, these two vectors are not multiples of each other, and therefore these two are linearly independent vectors. This is one example that we had taken in the past, and we proved that these two vectors are linearly independent, and therefore this will be a, and the, if you take the linear combination of this 2 1 1 2 vector, you are going to span the entire 2 dimensional plane, and therefore this is a basis for R2. Right, that is a basis for R2. Therefore, extend this, I mean we can actually look at Rn, vector space Rn. So, I am going to define my basis here. B1 is this set of vectors 1, all other n minus 1 components 0. So, basically this is n, then the second component alone is 1, the rest of all the components is 0, etc. We go to all the components being 0 except the last component 1. This is going to be a basis for Rn. Yeah. And what is interesting is this basis and this basis that we see here, these are called as the standard ordered basis. What we want is, we want basis which is, I mean we want to look at not the standard ordered basis which is always there, we want to look at different basis for a vector space, right, that is what we are going to look at. For this is for R2 and this is for Rn respectively. Right, this is what we have. Okay. Now let us look at some more stuff. So remember we also looked at the vector space of polynomials. We said that suppose we take P2 of x to be the vector space of polynomials of degree less than or equal to 2, vector space of polynomials of degree less than or equal to 2, then the basis for this is basically given by that means what we are going to look at the set of all those polynomials of this form a0 plus a1x plus a2x squared, a0 a1 a2 real. So the basis is going to be 1 x squared. Another basis for this B1, another basis for this is basically x squared x minus 1 x plus 1. You can check that this is a linearly independent set. So what you do is we take basically the coordinate vector corresponding to this, coordinate vector corresponding to 1 x squared. So coordinate vectors are 0 0 1 corresponding to x squared, x minus 1 has a coordinate vector which is minus 1 0 minus 1 1 0 and x plus 1 has a coordinate vector which is 1 1 0. Now you can put all these three in a matrix and then check whether it is a basis or not by looking at the homogeneous system of equations and solving and checking whether it is only the trivial solution that we get, right. Now what is more interesting is two things. Number one, suppose if B is equal to B1, B2 etc. Bn, then it is a basis for Rn any vector u in Rn has a basis expansion u in Rn has a basis expansion given by u is equal to alpha 1 b1 plus alpha 2 b2. Our task is basically to find these alphas, which we already know. When we said linear combination of vectors, all we need to do is put these b1 b2 bn in the matrix and then figure out the values of scalars, which is basically alpha 1 alpha 2 etc. Is that clear? This is called the basis expansion. Let us take a quick example and then go ahead. Let us take a quick example. Suppose I have example, let u1, let u be this vector 4 5 and let B be the basis for R2. I am going to consider the vector space to be R2, the basis for which is let us say 2 1 1 2. Now what we want to look at the basis expansion for this. So I want to find out scalars alpha 1 into 2 1 plus alpha 2 into 1 2 such that this is equal to 4 5. Now if we solve, we can see that alpha 1 is equal to 1 and alpha 2 is equal to 2. Alpha 1 is equal to 1 and alpha 2 is equal to 2 will give this. So we have 1 into 2 1 plus 2 into 1 2, which basically gives 2 plus 2 4 and 1 plus 4 5. So you get 4 5, right. You can figure out in any other basis, you can solve and then get the scalars corresponding to that particular basis that you choose. For example, we can try this, try this. So this is, you can probably solve and then get back. We are going to look at the same vector u, which is 4 5. I am going to look at vector space to be R2 and I am going to look at a second basis, which is basically say 3 4 minus 1 2. You can verify that 4 5 is equal to 13 by 10 into 3 4 minus 1 by 10 into minus 1 2. Please verify this, right. This is another interesting thing. Now let us look at couple of more interesting topics and then wind up the lecture. So the first one that we are going to look at is consider, I am going to look at what is called as an orthonormal set of vectors. Consider when let you have B, which is basically set of orthonormal vectors, which has this set of vectors phi 1, phi 2 etc. phi n, all of them are orthonormal. What do we mean by orthonormal? Set of, let us write that, set of orthonormal vectors, that is phi I dot phi j is equal to 0 if I is not equal to 0 j sorry if I is not equal to j and is equal to 1 if I is equal to j. The first condition says this is orthogonal, this condition corresponds to orthogonal. This says the length of the vector is 1, length is equal to 1, we have this orthonormal vectors. So, what we do is we are going to make the statement, we are going to say that a set of orthonormal vectors is a linearly independent set, a set of orthonormal vectors is a linearly independent set. Now, what do we mean by that? We have say alpha 1 phi 1 plus alpha 2 phi 2 plus etcetera alpha n phi n is equal to the 0 vector for alpha I is real, if and only if, I mean that implies alpha 1 is equal to alpha 2 is equal to etcetera alpha n is equal to 0. Now, how do we prove this? It is easy to prove because all we do is we take the dot product, of phi 1 with this, with let us call this as let us say equation star with star. So, what do we get? We get phi 1 dot alpha 1 phi 1 plus alpha 2 phi 2 etcetera plus alpha n phi n is equal to phi 1 dot 0. This is going to be dot product with 0. So, you are going to get 0. What we have? This is going to be alpha 1 because phi 1 dot phi 1 is going to be 1, which is already known, plus alpha 2 phi 2 dot phi 1, that is going to be 0. So, alpha phi 2 dot phi 1 into alpha 2 plus etcetera plus alpha n phi n dot phi 1, that is equal to 0. Now, all these fellows are 0, which implies alpha 1 is equal to 0. Similarly, we can prove we can establish all the alpha is to be 0. Thus, a set of orthonormal vectors is a linearly independent set. And it is interesting to see that if you want to expand this, since it is a linearly independent set, the set of these orthonormal vectors will basically span, it will have its own span, and that will be a vector space. Therefore, this orthonormal set of vectors will be a basis for the vector space, right. So, what we are going to say, if phi 1 phi 2 etcetera phi n is set of n orthonormal vectors in Rn, they form a basis for Rn. And what is interesting is how do we get the basis for the basis expansion is basically given by basis expansion, okay, orthonormal basis expansion. Let us do that, orthonormal basis expansion for a vector u in Rn. So, we have u is equal to alpha 1 phi 1 plus etcetera plus alpha n phi n. Now, if I want to get the coefficients alpha 1, all I do is I take u dot phi 1, which basically gives me alpha 1 phi 1 dot phi 1 plus the rest of the terms are all 0. Why? Because phi 2 dot phi 1 is 0, phi 3 dot phi 1 is 0, phi n dot phi 1 is 0. So, everything is 0. So, what are we going to have? I am just going to have this one, and what is phi 1 dot phi 1? Phi 1 dot phi 1 is 1, which implies alpha 1 is equal to u dot phi 1. Similarly, alpha 2 is equal to u dot phi 2, right, etc. Therefore, what we have is the expansion, orthonormal basis expansion for u is nothing but u dot phi 1 into phi 1 plus u dot phi 2 into phi 2 plus etcetera u dot phi n into phi n, and this is what we call as the Fourier basis expansion or Fourier expansion. People who have done Fourier series, you can actually see that in order to get the coefficient Can, you precisely do this. You take the function, the periodic function that you have An is equal to this integral over the period, you have f of t cos n t, you have that. So, you basically try to take the inner product there also. That is exactly what you have done. You have taken the dot product, you have also taken the dot product here. There cos m cos n are orthogonal functions, cos and sin are orthogonal functions. So, everything fits well. So, this is called the expansion in terms of orthonormal basis is called the Fourier basis expansion or Fourier expansion, right. Now, what is more interesting and important is, if you recollect, when we did this R2, we showed that 1001 is a basis for R2, 2112 is also a basis for R2, then we took 2 3 and minus 1 4, that also was a basis for R2. So, any set of 2 linearly independent vectors was a basis for R2. I mean, if you take any set of 2 linearly independent 2 component vectors, I mean your vectors must be from of course R2, we said that it is a basis for R2. So, now what we are going to do is we are going to define what is called as dimension of a vector space or a subspace, dimension of a vector space or a subspace. I mean it holds good for vector space also. So, what we say, the number of elements in the basis, the number of elements in a basis for a vector space V is called the dimension of the vector space. It's called the dimension of V. Okay. For example, B is equal to, let us say 2 1 1 2, right, and we looked at V, the vector space was basically R2. So, this number that you have is the same as the number of vectors in the basis that you will see, and what we are going to do is we are going to make a few statements here. We all know that the basis is going to be a linearly independent set of vectors which spans a vector space. So, what we have is we are going to say that suppose W is a subspace of V, subspace of, let us say, a k dimensional vector space V with basis for W having D elements, then W is a d-dimensional subspace of W is a d-dimensional subspace of V. Okay. And let us just quickly consider a few examples. Suppose if I have W to be this subspace which just contains the 0 vector, this is a subspace of Rn. So, let us say vector space V is equal to Rn. Now, the only vector that is there in W is the 0 vector, and that is a linearly dependent set. So, we want a subset of this vector space W which is going to be linearly independent. The only other subspace that you have, the subset of W that you have, is the empty set. If you remove this, the other subset of your W is basically the empty set. Therefore, what we say is the basis for the 0 dimensional space, the basis for W is equal to 0 is the empty set. Hence, the vector subspace W is equal to 0 is called as a 0 dimensional subspace, called a 0 dimensional subspace of Rn. Let us quickly make one or two comments and before we wind up. Any line passing through the origin, any line passing through the origin is a one dimensional subspace of Rn one D subspace of Rn any plane passing through the origin is a 2D subspace of Rn. Is that clear? So, what did we learn in this module? We basically looked at the idea of the vector spaces, vector subspaces, linear combination of vectors. We looked at linear independence, and then we looked at basis for a vector space and the dimension of a vector space. The basis was basically a generating set which helped us whose linear combination actually we could get whose I mean the entire vector space. So, that formed the basis, and the number of elements in the basis is going to be the dimension of the vector space. And we said that for the 0 subspace that we have, there is no I mean the basis vector contains only the empty set, because the only other subset of your W that you have, which is basically which contains the 0 vector, that means the 0 subspace is just the empty set, and therefore that forms the basis for your vector subspace which contains only the 0 vector, and we call that to be a 0 dimensional subspace and so on. Let us just try to spend some more time to understand what this basis means and what it actually geometrically to say that okay, this is the basis and this is the orthonormal basis, and we had the standard ordered basis of 1 0 0 1 and stuff. Let us just quickly look at geometry and then try to interpret it in a manner which we will understand better. Okay. So, let us just consider this. So, consider, let us say the standard ordered basis for R2, consider R2. So, the vector space that I am going to look at is R2. So, what am I going to do is we are going to look at R2 and let us say let us look at this. Let B1 be this basis which is let us say 1 0 and let us say 0 1 for R2. Right, this is the basis that we considered. So, let us look at how geometrically this 1 0 0 1 basis looks. We already know that 1 0 0 1 basically 1 0 corresponds to let us say this, and okay, this is 1 comma 0. So, this is basically the vector along this direction that we have, and 0 1 is basically this vector. So, that is a 0 1 vector, and this is going to be the direction of this vector, and this is going to be the direction of this vector. Now, this is something which we already have seen. So, if you have this is 1 0 0 1 basis, like all of us would have seen graph sheets where you would have seen this unit square, your graph sheets being kind of filled with tiles of unit square and stuff, right, and you see this orthogonal basis vectors here. Suppose I take this basis B2, let's look at this basis B2 which is basically say 2 1 1 2. Now 2 1 1 2, if I take this as a basis, so how is the axis going to look like? We will superimpose that axis on this this particular stuff that we have used, and let us see how it goes, right. So, let us first draw our usual standard basis, and then let us see how this goes. So, I have this, I have my 1 0 0 1 axis, I mean E1 E2 axis, let me call this as 1 0, and let me call that as let us say 0 1. So, I have my standard unit square, right. The graph is going to look like this, right. Now, I want to do 2 1 1 2. So, how does this 2 1 1 2 basis look like? So, 2 1 1 2. So, 2 1, if we take 2 1, this vector is here, this is 2 1, and 1 2 1 2 vector is let us say it is here. So, the 1 2 vector goes here. Now, if we see the next 1 2 vector would be basically here, the next 2 1 vector would be, okay, I will take it this way, it goes to 3 3, and so what happens if you see, we will see that the new graph is going to look something like this. The new graph that we are going to have, it is going to look like tiles of parallelogram. So, the new basis we take will basically look like this. So, let us take this. So, I am just going to draw a few more of this. So, let us take here, here, and so on. So, if I erase the standard basis stuff, the new graph is going to look something like this. Now, why is this graph looking like this? This is because the vectors that we have taken, namely the 2 1, the vectors that we have taken 2 1 and 1 2, they are linearly independent and they are not orthogonal. So, if you choose this 2 1 1 2 basis, the new graph sheet is going to look like tiles of parallelograms rather than tiles, square tiles. It is going to have parallelogram tiles. That means anything that you have on the rectangular tiles, on the square tiles that you have here, it is going to get stretched, it is going to get some kind of shear that is going to happen here. So, the shape is going to change here. For example, you have a circle here, this could actually become an ellipse like this, right. So, the new way of the basis is, as we said, it is basically another coordinate system that you are going to look at, that you are going to use to look at the data, right. So, if you look at B1 basis that we have here, here everything seems to be fine because the bases themselves are orthogonal to each other and of unit length, whereas here you see it is 2 1 1 2, which is not orthogonal and they are not also unit length. So, the graph is going to look something like this. Now, how else can we understand the basis? So, it's simply it's more or less like this, like you the standard basis that you have 1 0 0 1 is like the plain glass that everybody wears with no power and other things. It is just like the plain spectacles that we wear through which we see. Whereas, if you want a clear picture of what you are going to see, it is dependent on the individual eyesight. So, you choose a different lens to view your the objects, so that you get a clear picture of the objects, and that is exactly what your basis does. So, your basis actually helps you, the choice of the basis helps you look at the data in that perspective where in which the structure of the data is properly revealed, the internal structure or the inherent structure of the data is properly revealed. So, that is the idea of basis, and in fact, if we see when we do singular value decomposition and probably even principal component analysis, we see that they give you the best basis to view the data. In fact, it is a signal dependent basis, we say the data, it is dependent on the data. So, it is not that this 1001 basis that we use here for 2 dimension, it is independent of the data. So, that basis is always there, whereas what we want is we want to look at the data from that perspective wherein which we get some interesting ideas. You will see later when principal component analysis is being done in detail that even if you have the data cloud to be like an elliptical cloud or whatever. Now, when you choose a different basis, you see that maximum the data with maximum variance is basically captured. That means the direction along which the maximum variance is there, that is basically chosen as your first principal axis and stuff. So, another example is like basically, okay, you have some word in English which probably we in a simpler English, I mean when the word is uttered we really do not know what the meaning of it. So, what you do is you try to find out the synonym of the word and then try to understand. So, you basically have different words which could convey the same meaning. So, you want to figure out that word which will give you the meaning of this the complicated word that you look at. So, it is basically basis says that look, these are the axes through which if you see the data you are going to get a better representation, or you are going to get the structure of the data to be revealed, and that is the advantage of your this various bases that you have. So, you have infinitely many bases for a vector space. The search is for, or the hunt is on for finding out the best basis to view the particular data that you have, and that is the insight about the basis. Now, where do we go from here? In the next module that we are going to look at, we will study that the various subspaces associated with the matrix. Let us say we have a matrix A m by n. We are going to look at what are the subspaces, fundamental subspaces associated with this matrix, and we are going to get into a very interesting concept where we are going to look at the dimension of the subspaces associated with the matrix, one of which is what we are going to call as the rank of the matrix. So, in the next module we will look at the 4 fundamental subspaces associated with the matrix. Then we look at rank and what is called as nullity, and we will also look at what is known as rank nullity theorem, and we will also look at a couple of other subspaces associated with these matrices. We will try to look at eigen subspaces, and we will also try to look at inner product subspaces. Thank you.